to vibration or silent mode. We appreciate your cooperation. Ladies and gentlemen, let's give a word of applause for Minister Wu. Welcome, Minister Wu.
我们这个长得蛮像，两个人分辨不出太出来。还是我演哦，对啊，今天来的最大的关就是他吴成文而已，没有其他人。
Welcome to the Future Tech Pavilion FuTech. FuTech is co-organized by the National Science and Technology Council and other relevant ministries. This year, FuTech is themed AI cross-disciplinary applications and innovative breakthroughs, showcasing cutting-edge research achievements from various fields, both domestically and internationally, creating the most anticipated science and technology event of the year. 国科会吴主委，还有运动部黄启煌次长、中研院的陈君厚秘书长、卫福部的刘明勋技监，还有教育部的徐正邦副司长，以及呢我们现场的贵宾、媒体朋友们，大家午安，大家好，欢迎各位莅临由国科会携手中研院、教育部、卫福部及运动部打造的未来科技馆。那么今年呢，我们以 AI 跨域应用、创新突破为主题，汇集了海内外各领域前瞻科研的成果，打造了全年度最让人期待的科技盛会。And today we are very delighted to welcome distinguished international guests to this grand event. And please allow me to introduce them and give them a big round of applause. First, our speakers for today's Smart Robotics Forum. Let's give a word of applause to welcome Professor Tommy Asford from the Institute for Anthropomatics and Robotics for Koshiro at Institute of Technology. Welcome, Professor. And next, let's welcome Professor Atsuo Takanishi from Department of Modern Mechanical Engineering and Humanoid Robotics Institute at Waseda University. Welcome. Welcome, Dr. Stan Birchfield from NVIDIA. Welcome. Next, let's welcome Professor Karen Liu from Department of Computer Science at Stanford University. Welcome. Besides our speakers, we also have friends from overseas joining us. So if you're here, please stand up and wave to everyone. Once again, thank you for coming. Please give them a warm applause. Thank you. And next, we would like to invite our esteemed leader, Minister Chen Wei-Lu, to the stage for a few words. 让我们掌声欢迎国科会的吴成文主委上台为我们致辞。欢迎主委。
Good afternoon, all the distinguished guests, ladies and gentlemen. It's really my honor, pleasure, privilege to be here to welcome you to this very important event, the opening of the FuTech Pavilion. And I would like to thank Professor Yue Wenhong, the Director General of the Engineering Division, for National Science and Technology Council for organizing a very important forum for smart robotics this afternoon. And for this pavilion, I would also like to thank the partners of National Science and Technology Council, including the Academia Sinica and the Ministry of Education, and Ministry of Health and Welfare, and Ministry of Sport. So you can see the demonstrations, the booths from all these partners, all gathering here. Very important, showing very important research results, which can be realized and utilized for the industries and like all sectors of the society. And I would also like to thank our distinguished speakers, including Professor Takanishi from Waseda University, and Professor Liu from Stanford University, and Dr. Birchfield from NVIDIA, and Professor Fu from National Taiwan University, and also Professor Ashford from Karlsruhe Institute of Technology. Thank you very much for joining us today. And I think all the audience gathered here are waiting for your very distinguished speech later on for the important forum of smart robotics. On behalf of the Executive Yuan of Taiwan, I would like to let our guests today to know that our government has formally approved a very important national program for smart robotics, and the program will be conducted by several ministries and councils in our government, not just National Science and Technology Council, but also Ministry of Economic Affairs, the Ministry of Digital Affairs, the Ministry of Health and Welfare, and Ministry of Agriculture, and so on, so many education as well. So many ministries joining together for the benefit of the society, of the people, to develop industries that can help serve people for the future. So the emphasis of the smart robotics program for our country will be focused on service robotics. Service robotics for all kinds of services that human men, the humanity, for all kinds of humanity needs to serve all people. For service robotics, we emphasize not the original robotics industry, which is for manufacturing, but we emphasize AI and how to transfer human knowledge, human intelligence to the machine, and then can deal with all kinds of needs that can serve people. For even disaster prevention and recovery, which we had just encountered in Hualien the past few weeks, and for saving lives, for helping people to prevent even traffic accidents, to serve very dangerous works that originally done by human beings, but it's too dangerous, so that we can use machine to do the jobs. All kinds of needs for the society. It's the main purpose for the National Robotics Program. So we emphasize very innovative AI-enabled applications and systems, services to help human beings. So we are integrating all different expertise to help come up with systems, not just components.
哦，好。
So in Taiwan, in the past,
好，
we're focusing on
好
more on the manufacturing side. ODMs and OEMs industries, EMS industries. However, in the future, based on the existing hardware manufacturing expertise that we have today, we would like to invite international collaboration partners so that we can develop smart systems that can help people, as I mentioned. And for that purpose, we need to collaborate with so many different partners from all over the world. That is why we have this forum in the afternoon, this afternoon. And we also are showing different research and technology, scientific research and technology development results in this event in the next few days. We also invite everybody to take a look at them because that shows the results from different ministries and council. They invested in science and technology in the past few years and showing the results here. So we also invite our international visitors here to take a look to see how Taiwan can collaborate with you together to make the world better in the future. So once again, I would like to thank everybody to join us today, and I hope that for all the visitors today here, you have a very wonderful day and fruitful event in the next couple of hours, listening to the speeches of our distinguished speakers here. And please enjoy the show, and I hope everybody can have something that you can take away to make Taiwan and the entire world better in the future. Thank you very much.
Thank you, Minister Wu, for the inspiring remarks. Please proceed. 感谢主委的致辞，请主委先回座。Today, we are very delighted to have our distinguished guests from abroad and from various sectors join us to witness the pioneering technological outcomes at the Future Tech Pavilion. And next, we would like to invite our guests to the stage for a group photo in the following order. 我们今天现场有来自许多远道而来的朋友参与，那么难得的机会呢，有产官学研界聚集在未来科技馆。接下来呢，我们要先来进行今天的大合影。首先呢，让我们要邀请到国科会吴成文主委，接着邀请国科会苏正刚副主委，接着邀请科技办张正豪执行秘书。接着邀请中研院陈君厚秘书长，继续要邀请卫福部刘明勋技监，接着邀请教育部徐正芳副司长。And next, we would like to invite our distinguished foreign guest. Let's welcome Professor Tommy Asfor. Welcome. And Professor Atsuo Takanishi. Welcome Dr. Stan Birchfield. And Professor Karen Liu. And Professor Li Chunfu. 以及国科会工程处的洪岳文处长。好，请各位贵宾看向正中间，挥手的这台相机 ，Please look towards the center camera. And on one more photo, maybe we can make a thumb up gesture， 比一个大大的赞，给我们的未来科技馆。好，我们摄影师 OK 吗？好，接下来呢，我们邀请第二阶段的合影贵宾上台。首先欢迎产学处林德生处长，竹科管理局吴世敏局长，中科管理局许茂兴局长，南科管理局郑秀荣局长，前瞻处蔡妙慈处长，资讯处周子仁处长，自然处赖明 处黄俊如处长，科国处李旺龙处长，生科处涂君颖副处长，国家太空中心吴宗信主任，以及国家灾害防救科技中心陈宏宇主任，还有国家同步辐射研究中心徐家宏主任。好，我们再次邀请贵宾看向正中间挥手的这台相机 ，Please look toward the center camera。好，我们用第二张比一个大大的赞 ，Please make a thumb up gesture to the camera。And one more, please look your left side this camera. 好，我们还有媒体朋友们需要补充的吗？Your right side. Okay, please look at the center again. 好，我们现场摄影师都 OK 了吗？那我们再次的感谢我们台上所有的贵宾。论坛，我们的开幕论坛活动呢，将聚焦在智慧机器人发展趋势。那么第一场主题演讲呢，我们非常的荣幸哦，邀请到人形机器人领域的国际权威。那么他所领导的团队呢，开发出了可以在真实环境中与人协作的人形机器人。今天呢，将为我们带来的主题是人形机器人迈向通用型智慧的未来。Now we proceed to today's opening forum, and today's event focuses on trends in intelligent robotics. So for our first keynote, we're honored to invite an international authority in humanoid robotics, Professor Tommy Asfor. Let's give a word of applause to welcome Professor Tommy Asfor.
Yeah, good afternoon, everybody. It's an honor and pleasure for me to be here. Thanks a lot for the National Science and Technology Council for inviting me and for giving me this opportunity to learn about Taiwan, about technology in Taiwan, about the motivation of young people working on smart robots in Taiwan here, and for the REACH program, what the organizers put together to give us an idea about robotics and AI research here in Taiwan. So in the next 20 minutes, I will give you a brief overview about why I think humanoid robotics is so important for our society and for our economy. As you know, robotics is everywhere. Robotics is changing the way how we work and how we live. And if you see here these examples, robotics in production, in exploration, in construction, agriculture, in medicine. But if you look at these systems, every system has been developed in order to perform a task in a perfect way. A robot for production cannot do agriculture tasks. A robot for logistics cannot do medical robotics tasks. And this is what we would like to change with humanoid robotics. Humanoid robotics are versatile machines. This means these are machines which are able to perform a wide variety of tasks. And one day, any task what a human can do and maybe better. And the goal of our research is actually to understand the versatility of the human body and the motion intelligence of the human body. Why are we as humans so performant and can do so many things with the same embodiment, and why we are still not able actually to build technical systems in form of humanoid robots which can do the same. So we are interested in building general purpose machines which can perform any task what a human can do in order to improve and to contribute to a better quality of life of humans. And in the last year, I added the last item point on this slide, which I have been using in the last 25 years. Humanoid robotics is a multi-trillion market. projections tell us that the market of humanoid robotics in 2035-40 will be as big as the market of automotive. What we are doing here, I have been working in this field since 25 years. These are the humanoid robots we developed at the Karlsruhe Institute of Technology in Germany. And in order to provide help and longer self-determined life for people at home. So you see here our labs, a kitchen environment where the robot should help anybody, any person in daily activities, provide versatile and personal assistance for humans at homes, but also for caregivers, for example, at nursing homes, hospitals, retirement homes. I will not go too much into the details of the research questions, but I would like to show you some examples some examples of the work we are doing. So you see here a humanoid robot performing tasks in a kitchen environment like loading the dishwasher, cleaning the table, or a humanoid robot helping a human to prepare dinner for two people, as you see on the right side, where the challenge is to map this natural language instruction, Amma, please help me to prepare dinner for two people, into motor actions. To have a robot which has an understanding about its own abilities, about the task, what it can perform, and the task which should be done by the human, for example. Since the robot cannot cut the salad, the human should cut the salad, but the robot can wipe the table, can pour the oil, and so on. And recently, we arrived at version 7 of our humanoid robots here, and the goal of this AMA Robot 7, the 7th generation, is to provide a system for caregivers in retirement homes. So where I believe, particularly in Europe and in Germany, this is a very severe problem and labor shortage in the area of healthcare, and therefore I believe here that humanoid robotics can provide a solution or can provide a sustainable solution for these societal challenges. So it's not only about building these systems, about the mechatronics of the systems. You see here additional cognitive abilities of the robot or sensory motor abilities of the robot. Robots at home should be able to deal with any object, to manipulate any object, anytime and anywhere. And you see here the abilities of the robot to handle deformable objects, but also to recognize the intention of the human in the context of handover tasks here, as you see here in these videos. And it is not only about developing the hardware and the operating system behind it, which is really challenging and which we have to master in this area, but it is about building the architectures behind these hardware, behind these machines, which allow us to understand natural language, which allow us to understand situation based on visual information, and to map instructions like help me to prepare dinner for two people into motor commands. And we believe here in this context that these architectures should be memory centered, and that the memory system in the human body or in the human brain is very crucial and very important. And this is why we started implementing a memory system for our cognitive architecture, in particular implementing a deep episodic memory with deep neural networks, which allow us to encode the experience of the robot and to recall this experience in a very efficient way in order, for example, to verbalize to humans something about the past or the robot. I'm not going about too much into the details, but this is how maybe this architecture works. The robot would collect everything what it perceives, the objects it perceives, the names of the objects, when it perceives or detects an object, how it grasps an object, how it manipulates it, where to place it. You see here an example. I will be away for a few minutes. Can you please tidy up? And the robot knows how to perform this task because it has plans which we encoded, for example, which was learned by the robot. And then the robot stores all camera images, the information about the objects we grasped, and so on, in order to be able to answer questions like, did you see the red cup? Yes, I last saw it on the table 10 minutes ago. Sorry. You see here how this episodic memory is built, and now Leonard is back.
Tell me what you just eat.
I was the multi-vitamin juice for the capital top.
How long did it take to grasp the green cup today in the afternoon?
It took about 1 minute.
Tell me which object you moved to the countertop yesterday at 2 p.m.
I moved the red cup.
When did you last see the red cup?
I saw it on December 9th at 14:56.
So this is a very simple example, and this is what we expect actually from robots which should act or should help us at home to be able to answer these questions. If we look into the data, what we need in order to build these models, our robot generates about 350 gigabytes per hour. This means about 3.1 petabyte per year. Of course, we are not using only the raw data, but latent representations of the data, so representations in smaller dimensional spaces. But though also in these spaces the data remains significant, and this is why we are investigating how mechanisms of forgetting what we know in humans can be implemented in order to build episodic memories for robots which are as efficient, as performant, maybe at some point, as human memory systems. So the next example for humanoids, and humanoids are general purpose machines, is actually to help humans in 3D jobs, or actually to replace humans in 3D jobs, in difficult, dangerous, and dirty jobs. And you see here some examples with the 6th generation of our robot, where on the one hand, the clickers. On the one hand, the robot is able to support or to assist a technician in repair and maintenance tasks. The robot is able to recognize when a human is in need of help based on the task information and based on the interpretation of the current situation. For example, all these tasks are tasks which require 2 people, as you see here, like lowering the guard, like setting up the ladder for the expert technician in order to inspect the conveyor belt from the top, or like placing the cart here at the right position with the tools which are needed for maintenance and repair tasks. Another example of dangerous jobs is decontamination of nuclear plants. And we see here how these decontamination tasks are done these days, where a human has to pick up objects in a box to clean them and to place them in another box. And we would like to remove this human from this environment. Yeah. And you see here how our robots are able to grasp and to manipulate difficult objects. This is about grasping of unknown objects in cluttered environments, and where the robots are also able to recognize failures and to recover from failures. I have to hurry up. The second part, what I am going to talk about, is how our robots learn from human observation. And since I'm running out of time and people are giving me signs from the back that I have to stop in 1 minute or 2 minutes, I will skip many of these exciting things where we collect data about how humans perform tasks, highly accurate data, and data about the motion of the human, but the motion of the objects, and where we can, with machine learning methods, segment these human demonstrations in elementary actions, which we call movement primitives, which can be used in order to implement complex tasks like prepare the dough, for example, or like cleaning the table. Let me skip this, how we learn actually these sparse representations of manipulation tasks based on visual information. Yeah, you see here, for example, the pouring task can be represented by very, very few key points of the demonstrations, which can be used in order to generalize to pouring in different cups and from different containers. You see here how this can be done also with very, very few number of demonstrations. So only 6 to 8 examples are needed in order to have the robot learning these bimanual coordinated or tightly coupled or loosely coupled manipulation tasks. Humanoid robots made progress, and we see a lot of new systems these days. The whole thing started at the Waseda University with the Robot 1 humanoid robot. And I need the next slide. And the question is not actually whether humanoid robots will be part of the society, but it's about the when. And we have, I see, 4 undeniable forces. The progress we are experiencing in AI, that we are able to manufacture these robots, so mass production is happening now, what Tesla, Figure, Unity are doing. Aging population and labor shortage, there is no other alternative for a solution, and the form factor wins. So our entire infrastructure is built for humanoid robots. And I can tell you, that some people in the room might doubt now and think what's telling me, but let me give you a few examples. 1995, people said internet is a thing. Nobody needs a smartphone in 27. AI cannot understand language, 21. And today, humanoids will not work. And you see here that actually the history is on my side. The history is on my side, and the data, they are always wrong. Yeah, we had all these things. So the next revolution is the fusion of humanoid robotics and AI. And with that, I have to stop here. Thank you for your attention.
Thank you, Professor, for your wonderful speech. Thank you. Please have a seat. And for our second keynote, we'll present humanoid robotics research and its application. We are honored to invite Professor Katsuo Takanishi. Let's give a warm round of applause for Professor Takanishi.
Hello. My name is Katsuo Takanishi from Waseda University, Japan. And okay, how can I fast forward? Okay, first, she's from Taiwan. She's my postdoc, very good collaborator in the lab, doing a research on human robots like this, musical robots, for long years. So this time she may help me a lot. And she's also PhD student. She's Japanese, and she's making a sort of pitching robot. So you can see the video. I hope it works. Like this, very fast. Have you ever seen this before? In this case, the robot is not only using actuator but also using a spring and its mass. So it's a sort of human how to perform the energy efficient motion. This is very, very important, I think. And she's a Chinese, and she also, he helped helps me a lot about doing research on not only human but also exhaustive skeleton or leg processes, intelligent ones. And by the way, he is the first guy who started humanoid research in history. Professor Ichiro Kato, my advisor. So unfortunately, he died in 1994, but he developed many types of humanoid. But these two robots are very famous. Robot 1 stands for Waseda robot number 1. The second one, Waseda robot number 2. The first one was built in 1973. That time, the speed is very slow. One step 45 seconds or even 1 minute. And step length is only 10 centimeters. But at that time, this is the first time in history the robot moved by itself. The second one is not working but playing a keyboard like this by reading a musical score about 1 meter away from the robot head. Okay, why a human robot? Professor Kato told me that making a human robot is knowing a human self from the viewpoint of engineers. This is a very important viewpoint that why we have been making human robots for long years. And the second one is robotics, one of the social technologies based on the human model. So after this, so we have a lot of models about the human self. So our design methodology can be based on that model in terms of engineering idea. So the second one is the making of human robot is a sort of grand challenge. So when I was a elementary school kid, so I watched television, the American astronaut standing on the surface of the moon. That's a big shock to me. So after that, I entered science and technology. And after that, I made a lot of different types of human robots like this. Okay, this is variant 2. But anyway, this robot was built about 20 years ago. But you can see the robot has a special pelvis mechanism. Nowadays, many robots are using that configuration. But at that time, no robot other than this has such kind of DOA configuration. And also the mass distribution and the length of the ring system are almost the same as human anatomy. So I still this robot is the most human-like human robot. And you can see that the robot, okay, this robot can fully extend the knee while walking by using the pelvis motion. This is the same as how the human is walking. So extend the knee is energy efficient walking than the robot like this. And also this robot can walk outside like this. Very smooth. And the important point about human science in terms of engineering is, so human has two peaks while walking. The flow reaction force in the vertical direction. So other apes, chimpanzee or gorilla, has only one peak. So this is a big difference between human and the other type of apes. But for example, the Guardian 2 has really two peaks like humans, while Guardian walk like this, like Ashimo's walking or something, always bending the knee. So this is a big difference. So by humanoid, we can confirm how human is moving. And also we make the foot more smaller than like human like this. And also human robot can be used as a dummy robot. So in this case, at that time, Hitachi was developing a sort of a system. So in the end of the stage, they want to use a apply to human, but it's still they are afraid of the some injury. So they ask us to use our human robot in order to replace the human with the human robot. And also human robot has so many sensors, so you can easily obtain many data if something happens, fall down or even fail falls working. And also my university has a human science department. We also collaborated with them. We first measure the human motion. It is a handicap, and one half of the body doesn't move, but we try to move the data to human robot like this. And also okay, anyway, the society needs to change the law. This is very important in order to accept those high technology to human society. So we especially apply to the government, change the traffic law to allow a humanoid to walk or run in the public road like this. We did in the Fukuoka prefecture. By the way, Fukuoka is where I was born. Okay. Okay, we also collaborated with the European collaborators like this, Professor Paolo Dario, Alan Beltos, and many other research groups. And our technology not only within university but also to distribute to companies like not only companies but also other governmental organizations, BT and Temzac and even Sony. We collaborated and we give them licenses. And also now, like Minister Wu mentioned about disaster. This is the same situation in Japan. So from the 2015, we did a sort of collaboration research within Japan. And this is one of my research laboratories alumni, Professor Hashimoto. Now he's a professor of Waseda too. So he made this kind of robot because he developed many human robot before. Now he is trying to make a disaster robot like this. And this is a sort of armor in order to protect the robot itself. And this is the most important part, the actuator. So we collaborated with Mitsubishi Heavy. They supplied us a lot of know-how how to make an actuator. So at that time we had a sort of small line in university, and we developed many different types of actuators like this. And just 2 weeks ago, we press released the new organization called Kyoha. So because the many good companies located in Kyoto, so the companies organized the new organization to really develop useful humanoid. And at that time, there are several industries. This is totally industry-driven project. And now many companies are asking us to join. And very sorry, only in Japanese. I don't have time to translate to English. But like this, many parts of the robot can be supplied by those Japanese companies. And one of the most important applications is disaster. because Japan is so many top in the world, having many different types of disasters. So the first thing that we have to concentrate is this. By the way, like a pitching robot, this robot is running like this using the spring mechanism. So this is this kind of motion can be energy efficiently done by using this kind of mechanism. And also my young colleague, Professor Otani, and also one of my young alumni developed this kind of two-leg chair. Because in the real environment, wheelchair cannot be used sometimes, like steps over here. So if the chair has this kind of two-leg mechanism, so you can go up the staircases like this. And this is also collaborated with the Japanese company, Tensu. Okay, and it's something like 20 years ago. And we moved this robot to Los Angeles. And there are many people get on that robot. He was a mayor of Los Angeles. I don't know if he's in the mayor. Maybe in the US it's impossible. And okay, this is my collaborator in research, a musical robot. I hope this robot can. Okay, you can enjoy the robot playing the field. This robot has two lungs, like humans. So this robot needs to breathe in order to continue the play. And you can see the lips, depending on the tone, the lips shape changes in order to make optimal sound. So that methodology was learned from a professional flautist. Okay, this is a saxophonist robot. Okay. By the way, this research is done by a German student. Now he's because he's a semi-professional saxophone player, so he made this robot. Okay, this robot is speech production robot. This is a collaboration with NTT, Japanese telephone company. So they want to have this kind of robot in order to do research on human, how human is producing speech. I hope you can see, this is Japanese way. This is going on, please. Okay, if you access to the lab web page, you can listen to the different speech by this robot. But anyway, speaking of human speech was very, very tough. So you can understand how human is, very greatly produce many types of motion like this performance. You need to be air tightness. This is very important. So this is IUA or the other types of speech production. So very, very hard to listen, but we just do that. And this is not a speech. This is a sort of drinking. Okay, this is a more mental related robot. Okay. The important thing is equations of emotion. So we need sort of equations in order to control robot precisely. But we believe that there should be a sort of equation for emotion. So this is our idea. After that, the robot performs like this. In the beginning, the robot sees a rainbow. Robot expresses the happiness. But the robot has many different sensors on the body. If you hit, the robot reacts almost real time. And the robot has two microphones in the middle of the ear. So the robot can localize the sound. And also, whenever a robot sees the rainbow, robot was abused, the robot becomes angry. But if the robot smells alcohol, in this case vodka, robot becomes happy because robot is drunk. But this robot has a similar lung system. So gradually robot becomes serious. Then, so this is a sort of how this kind of emotional robot reacts to the environment. And okay, I should skip. Okay, now we combine the emotion expression robot and Warrior 2. And you can see
还在进行中，
some gap.
再晚一点，现在那个
続きまして、びっくりした瞬間のマスオさん。
现在会议中，5点半。
You realize this very short gap. And this is another type.
芝刈り機の真似ね。
By the way, before the Corona pandemic, we collaborated like 10 years with the theater players. So the human robot can be useful for theater play. If you know Osamu Tezuka, in Japan he is a god of manga. And the one theater group is playing some of his manga in the theater. So this is it is impossible by human to mimic like this. Okay, he's a director of the theater play group, and we taught them how to make robot. So now they make this type of robotic mechanism by themselves. And now I'm in some kind of collaboration research center for twins. It's between Waseda and the Tokyo Women's Medical University. Okay, this is a very old research. But working together with dentist people, something like 40 years ago. So I developed this kind of chewing robot because they want to analyze human chewing motion without using human because it's a breaking of timer. Okay, sorry, I have to end. But like this, I have been doing a lot of human robot research like that. So I hope everyone here enjoy a lot. And in the future, Taiwan, Japan has some collaboration in terms of human robot like this. So we have a lot of applications like that. Thank you very much.
Thank you, Professor, for a wonderful speech. Thank you. Please take your seat. our third keynote, we're honored to invite Dr. Stan Birchfield from NVIDIA, and he will present 3D scene awareness for robotic manipulation. Let's give a warm round of applause for Dr. Stan Birchfield.
Hello, everyone. Okay, so we all want robots to do useful tasks for us, like make a cup of coffee. And I used to start talks like this by asking the question of whether we were really making progress. Because from one point of view, a decade of research and the systems look kind of similar. But we have entered a new era, as you know. So, I don't think that's the question anymore. We now have huge advances in hardware and software just in the last couple of years. We now have robots making coffee, but in a fundamentally different way. And now I think the questions are, we done, right? Is this the end of the research? And if not, what is missing? So I want to propose that we need, among other things, 3D scene awareness. The robot needs to be aware of its surroundings, and this is necessary to make sure the robots act safely, to make sure that their actions are interpretable, and also to deal with the data scarcity problem. So when we first started looking at 3D scene awareness about 10 years ago, we started with the problem of object pose estimation. Is this, okay. So about 10 years ago, we started looking at object pose estimation, and this led to the work on DOPE, which is deep object pose estimation. So we have a deep neural network, it processes an image, and detects all the instances of the object, as well as getting the 60 pose, which is the translation and the rotation parameters. And the output of the network has been fed to an off-the-shelf PMP algorithm, and this algorithm is robust to pose, occlusion, lighting, and so forth. We trained the network solely on synthetic data. We found that a mix of domain randomization and photorealistic data achieved the best results. We need synthetic data because it automatically gives us perfect 3D annotations, which is very hard to do with real data. And with that training, our network was then able to achieve state-of-the-art results, right, compared to previous works. And it was able to deal with extreme lighting changes, extreme poses, upside-down objects, and so forth. We then, so anyone in the world could download our code, they could run it in their lab, but only if they had the same objects that we had, and this is a problem, so we wanted to make it possible for anyone in the world to use our algorithm on their objects, and so we came up with this HOPE data set. We found some toy objects, we scanned them, the synthetic rendering is shown here at the bottom, and then we trained the model on all these objects, and so then anyone in the world could download our code with the pre-trained model weights, and they could also purchase these objects online and then do physical experiments in their lab with our code. So we're all about trying to enable other people to do their research, and so this is one of the early successes that we had. So DOPE solves the model-based problem when you already have a CAD model at training time. So you can train the network to work on that specific object. But what if you don't have that? We want foundation models. So a foundation model would enable you to do object pose estimation when you don't have the model at training time, only at test time. So this falls under the category of model-based tasks. But we also want to do model-free tasks. So if you don't have a CAD model at all, we want to be able to do 60 object pose estimation if you have a set of images of the object. So you can do static onboarding with the object sitting still on the table, or dynamic onboarding if you have the object, say, in your hand, for example. And this led to the handle data set. So we took a set of real objects, hardware tools, and kitchen instruments. We used a NERF-like process to do multi-view capture of these objects, and that enabled us to get very highly detailed, accurate 3D pixel-wise segmentation of these objects, as well as a segmentation of the handles of the objects for object affordances. And so our goal here was to support things like functional grasping. Both of these data sets, the hope data set and the handle data set, have been incorporated into the BOP challenge. So we partnered with the organizers of the BOP challenge, the benchmark for object pose. And our data sets support not only the model-based tasks, whether the objects are seen or unseen, but also the model-free tasks. So here we're showing the dynamic onboarding sequences of one of the hope objects. This led to our work on foundation pose. So this is a foundation model that is able to perform 60 object pose estimation on objects that it's never seen before at training time. So it handles it handles the model-based case, but it also handles model-free. So it'll also work if you don't have a CAD model at all. And it works on single images as well as videos. So it actually solves 4 different problems under the category of unseen. And as you can see here, we achieve state-of-the-art results on all 4 of those problems. So this is a render and compare algorithm. So at the bottom you see the input image, and then we render the CAD model at a particular pose. And then we can do this in parallel on a GPU for a large number of hypothesized poses. And then it runs through a 2-stage process. We have a pose refiner followed by a pose ranker. The pose refiner is a Siamese network. So it takes the input crop as well as the rendering, and then has some additional layers followed by transformers that output the delta rotation and delta translation to refine the pose. And then we do this in an iterative process until it converges. And you can see it runs in parallel on all these different poses to refine the hypotheses. And then the pose ranking network will take the output of that and perform a global assessment of all the poses that it sees in order to determine the absolute, determine the ranking from which it chooses the best pose. Okay, so we trained this model also on synthetic data only. So we use the Objaverse CAD models, and then we use LLM to add diverse textures to these objects, which enables a large-scale training data for training this network. And we were able to achieve first place on the BOP benchmark. And so we're still the #1 open source method on this benchmark. So you can go to our website, download our code, and you can use it in your lab. Okay, so this is an example of foundation pose running on a video sequence of these little YCD objects, and you can see that it does a good job of tracking these objects over time, even when there's severe occlusion. So if you notice the can behind the yellow mustard, even though it's severely occluded, we're still able to track it. Okay, so what if you don't have a CAD model? So this is where our bundle SDF system comes in. At the top you can see the input video sequence. We also have, we assume that you have a mask, a 2D mask of the object in the first frame. And then this is a SLAM-based system, so it simultaneously estimates the pose of the object in each frame, as well as performing a 3D reconstruction of all the pixels that are not occluded. So here, okay, so here are some example results. You can see the high fidelity that it achieves in preserving accurate geometry, the lengths of the table and the flatness of the table and so forth. It only reconstructs the pixels that it has seen. So in some of these videos, the person does not regress the object, and so some parts of the object are never revealed, and so we're not doing any hallucinating here, but otherwise we will be able to recover the entire geometry. Okay, and we're a research group, but we partner with our product groups at NVIDIA, and sometimes they will take our code and they will extend it and make it even better in various ways. And so this is an example of the Bundle SDF commercialized version of Bundle SDF, in which case they have extended the code to make it better able to handle transparent objects, reflective objects, symmetric and deformable objects, and so forth. So you can go here, you can download the code. Again, you can use it in your lab, not only in a research lab, but also for commercial purposes. Okay, so we can take this bundle SDF and we can plug it into Foundation Pose. And so instead of requiring a CAD model, even at test time, we can then take a set of reference images, produce a implicit representation of the object using a NERF-like process, and then using neural-based rendering, use that to replace the CAD model rendering inside Foundation Pose. Everything else remains the same. This enables us to run Foundation Pose on an object that is never seen before. So this object, we take a few reference images to perform that bundle SDF computation to get an implicit representation of the object, and then we can track the object over time, even though it doesn't have a CAD model. Here's another example of Foundation Pose doing model-free tracking on a set of objects that is never seen before, other than the reference images. Okay, and of course there are many applications for this type of technologies. You can imagine augmented reality where you can turn objects into games and so forth. But our real interest is in robotics. So this is a research project we did recently where we took Foundation Pose and applied it to human demonstrations in order to track the object that in the context of a task that the human was performing. And we also track the target object as well as the source object, and so we can get trajectories in a common coordinate frame, which we can then use to train a diffusion policy, and that enables the robot to perform tasks that were presented to it by human demonstration. So here we have, for example, pick and place tasks where there's a source object and the target object, and we want the robot to be able to manipulate them in certain ways according to the demonstrations. Okay, we can do pig and hole as well, insertion using Foundation Pose. So here we have a plug and a socket. We're tracking both of them using Foundation Pose and using that to perform the task. Foundation Pose can also be used to overcome the data scarcity problem. So here we have human demonstrations. Foundation Pose enables those demonstrations to be pulled into a simulator, and in the simulated world, we can then generate variations on the theme, and that enables us to have much larger training set than we would otherwise have. And then once we've trained the policy, we can then apply it to the real world because we have Foundation Pose matching the sim to real. Okay, but we're not only interested in object pose estimation, we also want to get a full 3D reconstruction of the environment. So some of our recent work is in that area. We recently revisited the classic stereo problem where you have a left and a right image and you want to match those images in order to get a dense pixel-wise depth map or disparity map. So if you'd asked me a few years ago, if you'd shown me an image like this, I would have assumed that it was the result of some sort of ground truth process, but this is actually the result of our algorithm. And you can see again the high detail, the fidelity, and again the denseness. So we're getting a result for every single pixel in the image. Compared to RGBD sensors, as you see on the left, our method on the right is able to do a better job of handling reflective surfaces and dark surfaces, and we also do a better job of preserving flatness of the table and that sort of thing. And again, here you can see the straightness of the lines and the 90-degree angle of the Kleenex box, and also the curvature of the mug and the handle and so forth. So again, much higher fidelity from a passive stereo algorithm. So the Foundation Stereo, it's a deep neural network. We leverage monocular depth estimation, and then we fine-tune that. Or we really adapt it. We adapt the monocular depth estimation in order to make it applicable to achieving metric depth estimation. And then after the matching, we have some follow-on blocks, conv GRU blocks that are able to refine the disparities to get the full output. We again train it only on synthetic data. So this is some examples of the data. And we achieved number one on the both the middleware and the ETH 3D data sets, or the benchmarks, worldwide benchmarks. And again, our method is still, even though it doesn't look like number one here, it's the number one method for which there's open source code available. So again, you can download our code, you can use it in your lab. Okay, so there are lots of robotic applications you can imagine using Foundation Stereo for. This is again the result of our algorithm, object to camera pose estimation, and so forth. We're also partnering with Meta, so they, with their Aria glasses, they're using Foundation Stereo to achieve depth estimation, and they're going to be talking about this more next week at the ICCD conference. Okay, well, I've lost control of the display. We're using Foundation Stereo and Foundation Pose in a lot of different research projects, and we're also partnering with companies that are doing bin picking and that sort of thing. So you saw some of these images and videos flash up here. Hopefully you can kind of make sense of them. We're also doing indiscriminate grasping and so forth. We also are interested in VLMs. So VLMs are notoriously not all that great at doing 3D queries. So if we want to know where an object is in 3D, we need to fine-tune the VLM on data with that information in it. And so here, a recent CB Para paper this year, we presented a data set called RoboSpatial that we used to fine-tune the VLM in order to get 3D, to do a better job of handling those 3D queries, answering the questions like where an object is and so forth. And so here you can see an example where we plug that into a robotic system. We're interested not only in perception, but also in control. So we have a QRobo. QRobo is our online motion generation system that avoids collisions. It's a collision-free generation system. You can, again, download this code and you can use it in your robot lab. We avoid collisions by modeling both the robot and the obstacles using spheres. Makes everything fast. This is QRobo running on a real robot, following a sequence of desired poses. We can run this on an embedded GPU in real time. And there's more research involved. Okay, but all of that requires us to have a full 3D reconstruction of the environment, and so we have done some work on that, and this is still an active research that we're doing. Just trying to show you, like, for example, some of the results that we can get using our 3D reconstruction algorithm. And almost done. The final thing I want to show you is just that we're working on a new version of QRobo. It's going to be available to the public soon, so stay tuned. It makes it easy to add cost and constraints for avoiding like interpenetration and making smoother motion and so forth. None of this would be possible without our amazing researchers in my group, as well as our interns and collaborators that work with us. So shout out to them. 3D awareness is crucial for robotics. I've listed shown you a bunch of tests that are sort of fall under that umbrella. Neural reconstruction is super powerful. We have found that synthetic data is able to achieve the sim-to-real transfer immediately on some applications, and we predict that that'll continue in the future with more applications. And foundation models are here. And just to reiterate that our software is available both for research and commercial use in many cases. So if you can't find what you need, let me know and I'll try to help you connect to the right person. Thank you very much.
Thank you, Dr. Mansfield, for your wonderful speech. Please be received. And for our fourth keynote, we are pleased to invite Professor Karen Liu, who will present the new frontier of psycho-intelligence in humanoid robotics. Let's give a round of applause for Professor Karen Liu. Welcome.
It's my great honor to come back to Taiwan to give a talk, talking about my favorite topic, humanoid robots. And the best thing about being the last speaker is the question has already been answered eloquently by our previous speakers. Why humanoid? I think I'm just going to skip that and everybody's on the same page now. The more interesting question to me is why now? This is definitely not the first time people are excited about humanoid, right? We have seen a lot of the hypes before, and they just died out eventually. What makes this time different? Next, that's what they told me to do. Is this the answer? Is it because of the AI this time around, humanoids will stick? Well, I think that answers parts of the question, but to me there are other, arguably more important factors at play. A lot of people would say high-density batteries, high-performance electric motors developed in the last decade, they are game changers. But there are a lot of other, often overlooked factors or enabling technologies, such as 3D printing, very cheap 3D printing, free online design tools, customizable PCBs, and just a cheap but still powerful optimized compute. All these new advances create this very welcoming environment for robot hobbyists to tinker, to iterate, to design, to develop robots very quickly and cheaply. And because of that, we in the last few years, we have seen a lot of hobbyists become startup founders. And this collective energy and momentum is why it's driving humanoid industry today. And I think that's the reason this time around is different. So what is our vision? We recently developed an animation system that can conceptualize our vision very well. Next. So this is a digital agent, but it is fully physically simulated from head to toes, including all the fingers. And this agent can see the world, see this virtual world, and also understand high-level natural language command. So here we ask the agent to set up a workspace. An agent will come up with a plan and figure out what important objects to interact in what order. And for example, you put a monitors on the desk, it knows that it has to face outward, not facing the wall. And we don't need to tell this agent to do any more details planning. It will figure out everything on itself because it is connected to a large language model, actually the LLM in this case. And we can ask agent to do other things. This long horizon task, asking it to pick up the shoes, to do laundry, and that's it. That's just sort of the autonomous agent we want to be able to realize in the real world. So that's our vision. And eventually, what we want to build next is a humanoid policy. And I think this is something that a lot of people share, this vision. We wanted this one policy that can do navigation, manipulation, locomotion from egocentric vision and human level natural language. Next. So how do we achieve this vision? Our bet is that we are going to solve the robotics problem using computer animation. And this is the best bet because this is the bet I know the best. My background is in computer graphics and doing animation. Next. So for example, in the past 2 decades, we've been building a lot of human digital agent models that can condition on interesting input modality, like in this case it would be audios, and input would be audio, output would be the human motion. Next. And during this exploration as a computer graphics researcher, I realized 2 things are really important. The first thing is not just the motion that we care about, we care about the interaction with the world. And also we want our motion to be physically generated. So what you're seeing here is not just a sequence of poses, it's a sequence of a joint torque. And then we use a physics engine to realize the kinematic motion. Next. So this is what we can do in computer animation today. Next. So it sounds like if we can already physically simulate a digital agent, all we need is just push to the real world, to do sim to real. So we have, can we go back to one slide? Yeah, so between human motion, between computer animation and humanoid policy, there are 4 really important gaps that we have to overcome in order to achieve the humanoid policy. And those 4 gaps next are embodiment gap,